Oh, that's right, this has animations. I hope that doesn't. Okay, so measurements. I think we all understand what a measurement is. A measurement is a quantitative observation. It's not just like, wow, that's a big building, but actually telling how tall it is. It has a number associated with it. So a measurement has two parts. It's got the number and the unit. In this example over here, is this little green square, measuring the width of it. The width is 1 centimeter. 1 is the number, centimeter is the unit. Here, this is a skinnier green rectangle. 1 millimeter, again, a number and a unit. It's important to have both parts. The number gives us a comparison, and the unit tells us the scale. Okay, if you go to McDonald's and you say, I'd like 5. They're like, meal number 5? No, I want 5. What are you going to get? 5 what? 5 ice cream cones? 5 orders of chicken nuggets? 5 medium drinks? It's important to say 5 of what? So the units are really, really important. In chemistry, we deal with really big numbers, really large numbers, and really, really small numbers. And they don't always fit on your calculator. And so we use a technique called scientific notation. Anybody done scientific notation before? A couple of you? Okay, my third son did it in 6th grade math. So, theoretically most of you have heard it, but maybe you've repressed that, and it's lurking deep in your subconscious or something. What we do for scientific notation is we take a number, we express it as a product of a number between 1 and 10 and the appropriate power of 10. We're essentially factoring out tens. Okay, so this big number here, 93 million, right? That is the same as 9.3 times 10 million. If you put that into your calculator, that's the same thing. So what we do is we factor out a whole bunch of tens. We're moving the decimal point over, essentially. We want to get a number between 1 and 10, and then that's times 10 raised to an appropriate power. So 10 raised to the 7th power is a 1 with 7 zeros after it. That's what 10 to the 7th means. The other way to think of it is it's 10 times 10 times 10, 7 times of those. So any number can be expressed this way. Is a product of a number between 1 and 10 times a power of 10, and that power can be positive or negative. The power of 10, as your book explains it, depends on the number of places in which the decimal point is moved and in which direction it is moved. This makes more sense when we do an example. The number of places we move it determines the power of 10. The direction determines whether it is positive or negative. If the decimal point gets moved to the left, the number is large. The power of 10 is positive. Okay, I was like, there's got to be examples here somewhere. Here we go. So 3.45. Where is the decimal point in that number? Is there a decimal point that's written? No, we don't see a decimal point, so we're going to assume it's at the end. And so what we're going to do is we're going to move that decimal point. Ooh, that's not a good color for these slides. Let's go with a dark red. We're going to move it over here and over here. We're moving it 2 places over. So we rewrite it over here with the decimal point after the first non-zero digit, 3.45. And then the exponent is going to be 2 because we moved the decimal point 2 places. So the way you remember positive, negative is you look at the number that you started with, 345. So if somebody gave you $345, would you be happy? I'd be happy. You know, it's not a ton of money, but hey, you know, it's more than I had before, right? So someone gives you a big amount of money, a large amount of money, you have positive feelings about that, right? Large number has a positive exponent. If the decimal point gets moved to the right, or if the number that we started with is small, then the power of 10 is negative. So here, again, we're going to move that decimal point. We're going to take it from here. Whoops. Forgot to push the button. We're going to take it from here. We're going to move it 1, 2 places. We put it after the first non-zero digit. So we've got 6.74 times 10. We moved it 2 places, and now it's a negative because this was a small number. If somebody gave you $0.0674, you're like, this is 6, almost 7 cents, woohoo, you know. You wouldn't be so positive about that. Small numbers have exponents that are negative. Large numbers have exponents that are positive. Concept check. Which of the following correctly expresses 7,882 in scientific notation? So this is a multiple choice question, and the questions on your exams are going to be multiple choice, and there are strategies to answering multiple choice questions. You can increase your chances of getting a correct answer even if you're not really sure what you're doing. So that's one thing that's kind of nice. Let's look at these and let's see if there are any of them that are obviously wrong. What is obviously wrong about letter B? The decimal point's in the wrong place. We have to have the decimal point after the first non-zero digit. So B is out because the decimal point's in the wrong number. In the wrong place. So look at the rest of them. Look at that original number, $7,882. I would love to get $7,000, right? That's a positive exponent number, right? So letter D can't be correct because it's got a negative exponent. So we can just get rid of that one. So now we've narrowed it down. If you're guessing, you've got a 50-50 chance of guessing correctly, but of course we're not going to just do that. How many decimal places, did that decimal point get moved? Well, the decimal point was here. What? Okay. The decimal point was here, and it moved 1, 2, 3 places. Okay? So then the correct answer is C. That's my children calling me. If they call back too many times, I'll have to answer it. Okay, any questions? So the correct answer is C. Let's do another one. Which of the following correctly expresses 0.0000496 in scientific notation? So one method of answering multiple choice questions is to look at the answers and eliminate obviously wrong ones. Some students find that if they look at a whole bunch of different answers, they start to get confused. And so you may find that it's better to just actually answer the question and then see if your answer matches up. So let's try that method on this one. So if we're going to turn this into scientific notation, we have to move that decimal point over, right? So we're going to have 4.96. And then we have to decide how many places did we move it. Well, 1, 2, 3, 4, 5. We moved it 5 places. So it's times 10, and it's a 5. And then we have to ask ourselves, Is it positive or negative? Is that a big number or a small number? That's a little teeny tiny number, 0.00000. So this is a negative 5. So we answer the question, and then we go looking for the answer among the choices given and which choice matches up. A. Again, D is wrong because the decimal point's in the wrong place. And then B and C just differ in the exponents a little bit different. Correct answer is A. And then this one says some more examples. So express these in scientific notation. Well, what's the coefficient part? It's going to be 1. Where do we put the decimal point? After the first non-zero digit, 1.25 times 10 to the something. Then we look at this number, and the decimal point originally was here. I don't know how it keeps doing that. It was here. And we go 1, 2, 3, 4. So we moved it 4 places. That's the number. Is it positive or negative? 12,500. Big number, small number? Big number, positive exponent. Okay, I'm going to have to get rid of all the animations on this. Let's just go through these. Oops, went too far. Dang it. Okay. Well, that's different ones yet. Okay. Yeah. 247. So we're going to write that as 2.47, right? 2.47 times 10 to the something times 10 to the 2. We move the decimal point over 2 places. 1, 2. 247 is kind of a big number, so it's a positive. 10. Well, we got to put the decimal point after the first non-zero digit. You could put the decimal point there, but you don't really need to put a decimal point, do you? But that's going to be 1 times 10. Oh, this seems weird, huh? The decimal point was here. The decimal point was here, and we moved it over 1 space. So 10 is the same as 1 times 10 to the 1. No, it seems a little ridiculous, but you can write any number in scientific notation. You can even write the number 1. 1 is 1 times 10 to the 0.
Do you have an example of one with a non-zero times 10 to the 0, which makes it the same number?
Well, yeah, if you had like the number 5, you wanted to write that in scientific notation, that would be 5 times 10 to the 0 power. Because 10 to the 0 is 1. Anything raised to the 0 power is 1. Now, we probably won't have to do things like that, but just in case. So this number, 3,500,000. So that's going to be 3.5 times 10. And then that decimal point's getting moved, right? Here it's from here to here is 3 and 6. So sometimes I get tired of counting all those little things. Again, that's a big number, positive exponent. 1,430. 1.43 times 10 to the what? To the 3rd. We move the decimal point over 3 places. That make sense? Okay, so here's some more examples. These are all little ones. So 0.135. Well, we have to move the decimal point after the first non-zero. So 1.35 times 10. How many places did we move it? Just one. Is that a big number or a small number? It's a small number, so the exponent is negative. If you have a TI-30XA calculator, you can get your calculator to do some of these for you. I would encourage you to do it yourself and then check your work with your calculator. If you have your calculator with you, you should pull it out. Other calculators allow you to do this too, but some of them are a lot more complicated. But for this number, if you put 0.135 into your calculator and then press that yellow second button and the number 5, which has SCI written above it, then your calculator will display 1.35 and a negative 0.1 up there. And that's your calculator's kind of shorthand way, baby talk, for what we wrote. So this is what your calculator would say. And so when you see something in the display of your calculator like that, and you write it down on your paper, you have to translate it back into human language, okay? Because that's calculator language. So when you write it down this way, okay, with the times 10 in there. To go from scientific notation back, you do the second button again, and the number 4. Above 4, it says FLO. FLO stands for floating decimal point, which allows the decimal point to go anywhere. And then it'll show you the 0.135 again. So you can kind of play around with that while we're doing these other examples. So 0.0024. So that's going to be 2.4 times 10 to the something, right? So we look at that, we move the decimal point 1, 2, 3 places, times 10 to the 3. And then we ask, is that big number, small number? It's a small number, minus 3. 0.104 becomes 1.04 times 10 to the, and we moved it 1 place, times 10 to the 1. It's a little number, a small number, it has a negative exponent. Okay, what's this one in scientific notation? 3.06 times 10 to the negative 2. Very good. How about this last guy? 7.2 times 10, and you're like, you gotta get your finger out and count, huh? 1, 2, 3, 4, 5, 6, 7. Negative 7. Okay? We are going to use scientific notation, and it is important that you understand what it means. Okay, if you see a number in scientific notation and it has a negative exponent, that means it's a small number. If it has a positive exponent, it's a big number. So let's talk real quick here about how to do this on your calculator. So this is where you need the EE or EXP button on your calculator. So hopefully you have your calculator with you. So that button means times 10 to the. Isn't that cool? I'm so happy I got this to work. You have no idea. Spent hours. The technology hell. So to enter a number on your calculator, let's do 1.5, that's a decimal point, 1.5 times 10 to the third. How do you enter that on your calculator? We have to learn how to do this because we're going to deal with some numbers. You can't just always convert to decimal notation and then type it in that way. Because when we get to numbers like Avogadro's number, 6.022 times 10 to the 23rd, your calculator can't handle it in decimal form. So we'll have to use scientific notation. So to enter this in your calculator, you press the 1 button and the decimal point and the 5, and then the EE. Some of you may have an EXP instead. That's okay. Occasionally you'll see a calculator that's times 10 to the something like that, a button. So let me know if your calculator is different, and I can help you. So 1.5, as you press EE, say to yourself, times 10 to the 3. You don't do 1.5 times 10 and then press the EE button. The EE button does that all for you. Okay? So if you do that and press equals, your calculator should show you this. Okay? And if it doesn't, it's probably your calculator being naughty, and I can help you. Does anybody need me to speak with their calculator? Yeah? There's always one renegade calculator in a classroom.
Alright, so I think I did it wrong. This is 1.5. EE.
Mm-hmm.
3
3.
equals.
Yep. There you go.
Oh, okay.
See, it's my presence. It makes the calculator behave. Anybody else? So let's try one with a negative exponent. Let's see. I'm going to get rid of this. It's in the way. So let's try 2.7 EE. And now here's where some calculators are a little different. Some want the negative sign first. It's on here. Come on. 2. There we go. Okay. Point. E. Come on. There it is. Okay. 2.7. Actually, let me back up a minute. I forgot to put the original number down. We're doing 2 times 7 times 2.7 times 10 to the minus, let's do 4. Okay, so that's going to be 2.7 EE, and then you should have a change sign button. It might look like plus minus, or mine looks like this, or it might be look like that. Come on, you're really close. You can talk faster than that. One of those buttons, you need to get the negative in there, and then you press, I've run out of room, 4. Okay, if you press equals, then you should see point 0, 0, 1, 2, 1, 2, 3, 4, point 0, 0, 0, 2, 7. Okay. So enter 2.7 times 10 to the minus 4th in your calculator, press the equal sign, and get it to display 0.00027. Anybody need me to stand next to their calculator and beam goodness onto it?
Do we need to put the 0.00? Do you want that?
For this, what you're doing is you're entering the 2.7, but your calculator will show you the 0.00.
You want that first 0?
If you write it down, I like the first 0. Most scientists are going to write a 0 before the decimal point. It kind of calls attention to the decimal point, especially if it's like 0.5. Well, if you're pencil's really sharp and hard, and it just makes a little tiny dot, you might not see it. If there's a 0 in front of the 5, we look at that and we're like, why would he write 05? Oh, maybe there's a decimal point there, and then we go looking for it. So the 0 in front of the decimal point just calls attention to the decimal point. When you enter a number like that into your calculator, 0.5, you don't actually have to type the 0 in, but it doesn't hurt. Some people just, no, but that's what it says, I have to push the 0. Fine, push the 0. It's not going to make any difference, except if it makes you feel better, you go right ahead and press the 0. So any questions about using your calculator? Okay. Oh, I don't think that's what I want to do. What do we want to do? Maybe if I just do that. Here we go. Oh yeah, we're cruising right along. The nature of measurements. Okay, we mentioned already that measurement is a quantitative observation, has two parts, the number and the scale, which is the unit. Examples, 20 grams. 20 is the number, grams is the unit. 6.63 times 10 to the minus 34 joule seconds. Okay, that's a weird unit, but it's a unit. It's kind of a weird number too. It's in scientific notation. But there's a number and a unit. Okay, and a common mistake that beginning chemistry students make is they leave the units off. Units are really important. There was a space mission, I forget exactly what it was. It was supposed to go up and orbit Mars, I think. And they, millions and billions of dollars. Tons of people working on this, and they launch it and everything, and it goes to orbit, and it starts getting closer and closer, and then it just falls in and crashes. It was supposed to orbit and send them data for a long, long time. What happened? Well, one team of scientists was using inches, and one team of scientists was using centimeters. And they didn't communicate the units that they were using, and so there was a serious flaw in the design, and it couldn't maintain orbit, and it was just this colossal waste of money. Units are very, very important. There are two widely used systems of units. The English system is what we use mainly in the United States. Interestingly, the English people don't use it very much anymore. And the metric system, which is used by most of the rest of the world.
Why didn't it ever transfer over? Because when I was in school, they were going to go totally metric, and then we never did.
Yeah. We don't like to change. I think, we're used to miles and inches and pounds, and we just don't want to change. There is significant cost involved in changing. It's not something where you can just decide, okay, we're going to use the metric system tomorrow. Get ready. Because you have equipment and tools and all kinds of things. And it's gradually creeping in, because you go to buy tools and there's metric wrenches and there's English wrenches with inches. And so it's coming, but it's coming far too slowly. And you look at a package like this says, the amount that's in here. 32 fluid ounces, 1 quart, 946 milliliters. So we're kind of in this dual position right now where we're kind of giving lip service to the metric system. And I think, a lot of people just don't really understand it, and so they don't like it, And I'm not a big fan of change unless it's my idea. If it's my idea to change, then I'm all for it. But if it's somebody else's idea that, no, we need to change, I'm like, no, what we've got is good. Just leave us alone. So I think it's just kind of an inertia thing, and it's what we had been doing. I think the longer it goes on, the harder it is to change. That's a very good question. Personally, once I learned the metric system, the English system is so much harder to use. I mean, it's just really, really a stupid system. It's archaic, really. So the metric system is very, very similar to what's called the International System or SI system of units, and that's what the scientific community uses. The differences between them are so subtle that it's really not even worth talking about. So as far as this class goes, the SI system and the metric system are one and the same. So in the SI system, they have fundamental units for different quantities. Mass is a kilogram. Length is measured in meters. Time is in seconds. That's one thing that's the same between the metric and the English system. Temperature is measured in kelvins, electric current in amperes. We won't even really talk about that. I don't know why they put it in here. An amount of substance is measured in moles. So those are just examples of SI units. What sets the SI system and the metric system apart from the English system mainly is the use of prefixes. In the English system, if you need different sized units, because measuring the distance from here to Minnesota in inches would result in a really, really big number, because it's like 2,500 miles. I know because my parents live in Minnesota and we've driven there. So 2,500 miles, I mean, that's a big number. You put that in inches, it's going to be this huge, ginormous number, and those are awkward to work with. And so we use a larger unit, like mile, to measure a bigger distance. But you wouldn't want to measure the width of my calculator in miles, because it just wouldn't be very meaningful. So in the English system, they have all these different units. There's inches and feet and yards, and I think furlongs, and then there's miles, and all these different units. And the relationships between them are really strange. There's 12 inches in a foot, and 3 feet in a yard. There's 5,280 feet in a mile. I can never remember the yard one. It's like 1,080 something. 760? 1,760, yeah. So all these weird numbers you have to remember, okay? And it's like, I can never remember how many tablespoons are in a cup, you know. I always end up having to use a calculator that does that for me. But these prefixes are all based on powers of 10. So they have this one set of prefixes, and we use them on all the units. So you memorize a few prefixes, and then you can make units of all kinds of different sizes, and it's all powers of 10. So hopefully you recognize that some of these are things that I put on that memorization quiz, right? Some of these will get used more often. Kilo and centi and milli, and I think I put micro on there. These are the ones that we use more often. Mega means a million. Kilo means 1,000. So a kilometer is 1,000 meters. Kilo is a prefix that multiplies whatever you put it in front of by 1,000. So we need to know the mathematical meaning of the prefix. We need to know its symbol, and we need to know its name. Okay? So the meaning can be expressed as a decimal number or as a power of 10. I personally think the powers of 10 are easier to remember. There is actually a prefix for every factor of 10. We don't list all of them in here, and most of them we don't use. We tend to use the ones that are powers of multiples of 3. 10 to the 6th, 10 to the 3rd, 10 to the minus 3rd, 10 to the minus 6th, 10 to the minus 12th. Those are the ones we tend to use more often. But those are the metric prefixes.
On the mass, is it technically measured in grams and then kilo is a prefix on that? Or
Right.
is it still kilograms?
Yeah. See, in the metric system has base units, and the SI system has base units. The SI system uses kilogram as its base unit, the metric for mass. The metric system uses gram. A kilogram is 1,000 grams. Okay, and you get to a higher level class, and they may quiz you, what is the base unit in the SI system? I really don't care. We just need to know what a kilogram is, what it measures, and how to convert it to grams. So I'm not going to get hung up on the details of those systems. But there's several quantities that we measure in chemistry. One of them is length, and the SI unit of length is the meter. And so this gives us the relationships between these different prefixes with meter. So here we have the meter. A kilometer, kilo means 1,000. So this is 1,000 meters. Another way to express 1,000 is 10 to the third. Decimal has to do with tenths. So a decimeter is a tenth. It's 0.1 meter or 10 to the minus 1 meter. Centi. How many cents are in a dollar? 100. A cent is 1/100th of a dollar. A centimeter is 1/100th of a meter. A millimeter is 1/1000th. A micrometer is, I don't want to even try to name that, it's 10 to the minus 6, and a nanometer is 10 to the minus 9. So the prefix just multiplies the unit and makes it either into a bigger unit or a smaller unit. Volume is related to length because you can take a cube and measure the length of each side and calculate the volume that way. Volume is a measure of three-dimensional space occupied by a substance. The SI unit is the cubic meter. A cubic meter is really big. A meter is about from my nose to my finger. And so, that big. It's really big. We don't deal with any volumes that large in chemistry lab.
Is it less than a yard?
It's a little bit more than a yard.
More than
Yeah, it's 39 inches approximately instead of 36. So it's a little bit bigger than a cubic yard. But that's a volume unit that we have a hard time picturing. But a cubic meter would be a cube that's 1 meter on a side. So if you took that meter and divided it into 10 spaces, you'd get a decimeter. Okay, so we take this, it's made out of all these cubes, and if we take one out of the corner that's 1/10 in each dimension, that's a cubic decimeter. It's the children again. Forgot to call them back during the break. Their big brother's home with them. They're fine. Probably asking me something silly like, where's the milk? It's on the door of the refrigerator, but I can't see it. Open your eyes. Children are funny. We all used to be children. Okay, anyway, a cubic decimeter. That has a special name called a liter. So when we, let me just keep going with that. So here's that cubic decimeter. It's 1/10 of a meter on a side, and if we blow that up so that we can divide each of those sides in 10, then we get a centimeter. And here we have a cubic centimeter, a cube that's 1 centimeter on a side. That is a much nicer little unit of volume. A cubic centimeter is the same as a milliliter. Okay, and in medicine, they abbreviate, I don't want the highlighter. They call it 1 cc for 1 cubic centimeter. And that is the same as 1 milliliter. So, in all those hospital shows, you will give him 5 cc's of this strat, right? 5 cc's. 5 cubic centimeters. It's the same as a milliliter. So when we talk about solids, we tend to talk about them in terms of length cubed. So a cubic centimeter, a cubic meter. And if we talk about liquids, we tend to use milliliters and liters as the volume. I think we all have a pretty good idea of how big 2 liters is, right? 2-liter bottle of soda. Okay, that's one metric thing that we've really kind of gotten used to. A liter is close to the same size as a quart. So we use liters and milliliters for liquid volume, cubic centimeters typically for solid volumes. And a liter is the same as a cubic decimeter. We don't use that relationship much at all. Mass is another thing we measure. Mass is similar to weight, but it's not the same. It's actually a measure of the amount of matter present in an object. The SI unit for that is kilogram, but the unit we use in chemistry is the gram. I'm wondering how many, I want to go to, I went too far. Okay. So here they're showing you a balance and finding, we often use the terms mass and weight. We'll say, well, we weighted on the balance and the mass is this. What is the difference between mass and weight? Weight is the force of attraction of gravity for an object. And so if you stay on the same planet, your mass and your weight are going to be equivalent. If you go to the moon, your weight's going to change, but your mass is not. You weigh 1/6 on the moon that you do on the Earth because the moon is smaller and its gravity is less. But you don't actually lose 1/6 of your body mass by going to the moon. It's important to have some concept of how big these metric units are. It was on the slide, I forgot to say anything about it. A kilogram is about 2.2 pounds. So kilograms and pounds are in the same ballpark. Meters and yards, same ballpark. A liter and a quart. So just to have some concept of how big these things are. And so then questions like this, which of these things doesn't make sense? A gallon of milk is equal to about 4 liters of milk. Is that true? About? Yeah, about. We're just really rough. A 200-pound man has a mass of about 90 kilograms. Yeah, because a kilogram is roughly 2 pounds, 2.2 pounds. So your mass, your weight in pounds is going to be larger than your mass in kilograms. A basketball player has a height of 7 meters tall. No, because a meter is like a yard, right? A yard is 3 feet, so this guy's 21 feet tall? I don't think so. Okay, so that one is ridiculous. A nickel is about 6.5 centimeters thick. How big is a centimeter? A centimeter is, an inch is 2.5 centimeters, 2.54. So, it's like a little less than half an inch. But is a nickel 6.5 of those? No. Okay, so it's very helpful to have a clue about how big these metric units are. That one's silly and that one's silly.